so for the introduction, actually, I really let me know it works. But I just want to say just welcome to the university, and I hope that we can give you a tour after the talk.
Thank you very much.
So, Miriam, please.
So I introduce you in Spanish. Es un honor tener al profesor Paolo Creminelli acá. Él hizo su doctorado en Pisa, en Italia, y luego se fue a Harvard a hacer su postdoctorado, y si recuerdo bien, desde 2005 está en ICTP como Research Scientist y trabaja en varios tópicos alrededor de cosmología y clasificación y dark energy. Y hoy va a decirnos sobre uno de los temas.
Sí.
Bienvenido.
Gracias. Muchas gracias. No, I speak English. So it's a great to be here. It's my first time in Colombia, and I'm having a good time. Okay, so let me. I take 5 minutes of your time to tell you where I come from, for reasons that will become clear. So unfortunately everything is cut, but so I come from ICTP, which means the International Center for Theoretical Physics. It's a place in Trieste. So Trieste is a town, this is Italy, and it's on the far east of Italy, close to the Slovenian border. And this is the sea, and this is ICTP. What is ICTP? So I just make some advertisement. Some people in the audience know very well, but it's a research institute. It's not a university, and it belongs to the United Nations. So it's part of UNESCO, which is part of the United Nations, and it's also funded by Italy in a large amount. It has been founded in 1964 by Abdus Salam, who is a Nobel Prize winner for the discovery of the Standard Model. Actually, he did his work about the Standard Model while he was a director of ICTP. Okay, so what is why I'm telling you this? So what is strange about ICTP? ICTP, this is our aim. The aim of ICTP is to foster the growth of advanced studies and research in physical and mathematical sciences, especially in support of excellence in the developing countries. Okay. So, in short, it means that ICTP has a substantial amount of money which is devoted to bring people from all over the world to ICTP in various activities that now I will explain. But in short, there are many conferences, many courses, and there are people really from all over the world coming there. So it's not so usually if you go to a conference, so some countries are well represented and many others not. At ICTP there is more balance because we have some money to invite people from all over the world. So these are the topics that we cover. So I belong to the first group, which is high energy cosmology and astroparticle physics. There is a group in condensed matter. There is a group in mathematics. There is a group in Earth system physics, which means seismology and weather. And there is a new group in quantitative life science. So what do we do with ICTP? Well, there are many conferences. So more or less there are 50 activities, like one every week. This means schools, conferences, workshops in Trieste. And as I said, there is quite a lot of money to bring people from all over the world. We also organize activities in different parts of the world, something like 15 every year. We have what is called a diploma program. So it is a program which is basically it's a one-year program, and the purpose is to bring people with different backgrounds to the level of going for a PhD wherever they want. And it is reserved to people from developing countries, broadly defined, and ICTP covers for everything, the travel and accommodation and everything during the stay. We have something like 40 students per year. We have a huge number of visitors, 6,000 every year. There are various ways in which people, researchers, can be affiliated to ICTP. They can come regularly to keep a relationship with people there and participating in these activities. This also works for students. STEP means sandwich program, which means that a PhD student will spend half of the time in his or her home country and half the rest in Italy. Apart from this, it's a standard research place where there are faculty, postdocs, PhD students, and so on. And just to conclude, I just want to mention that there are partner institutions. The biggest one is the one in Brazil, in Sao Paulo, which is, in some sense, is similar to STP, a bit smaller in size, but with the same kind of activities. And the new places are basically just born in Rwanda and in Mexico, so these are very small at the moment. So, okay, so this was, sorry, an introduction about myself and my institution. Now I come to the topic of the colloquium. Okay, so please don't feel shy to ask questions in any language. So, because of course I don't know the background and I don't want to get people lost immediately. So I'm going to talk about, I will explain basically these two concepts first of all. So I'm going to describe the recent wonderful experimental results in gravitational waves. I will explain what the gravitational wave is. And then I will talk about, as I will explain, we're going to learn a lot of physics from these observations. In this case, I'm focusing on a particular aspect, which is the one I work on, which is the connection between these observations and what is called dark energy, which I will explain. Okay? So let me start. Okay, so this is a the first detection of gravitational waves occurred a little more than 3 years ago, and it was done by 2 experiments back then. So these are 2 experiments called LIGO. These detectors are both in the US, very far away from each other. Since I'm Italian, I just want to stress that now there is another detector which is working, and as I will explain, it's very relevant, the presence of this third detector. This is called Virgo, and it's a similar detector near Pisa, which is the place where I started. So I have to make it.
Is it the same size, or?
It's approximately the same size. I mean, it's a border, I will explain, a border a few kilometers, around 4 kilometers. Yeah. So it's slightly less precise, not because we are in Italy. But I'm kidding. It's almost there in the sense that they are quite close in sensitivity. I stress this because getting funded in Italy is not the same as the US, which they have a lot of. I'm quite proud of friends that are working in Virgo, and they are able basically to collaborate. And it's a single collaboration actually. It's called the LIGO collaboration. Okay, so what are these objects? So you see that there are these 2 arms, which are a few kilometers in length, and inside these tunnels there are lasers. So there is light going back and forth because there is a mirror at the end. And what the detector does, as I will explain, is to compare, in some sense, the time it takes for light to go back and forth here to going back and forth in the other direction. Okay. You see that all the detectors there is this shape. So, what is a gravitational wave? What are we looking for? Okay. So, for students, a gravitational wave, you should think about it as, it is the analog of the electromagnetic wave, so the analog of light, but in the gravitational sector. So, it's not so easy to imagine that, but basically you should think about a wave which distorts space-time. Okay. So you see that the way to think about it is that as the wave progresses, it distorts space-time, let's say space, in the orthogonal direction. Okay? So it squeezes space either in that direction or after a cycle in this direction. Okay? Of course, we're talking about, as I will explain, very tiny effect. Okay? So how do you detect these gravitational waves? These gravitational waves are very, very, very tiny. why they are tiny? Well, because as you can imagine, gravity is a very weak force. Okay? We can only detect it only when we are in the presence of huge objects like the Earth, the Sun. But in general, when I talk about I mean, the interaction between small objects, gravity is completely negligible, and electromagnetism is huge in comparison. So that's why these waves, which were predicted by Einstein, by general relativity a long time ago, were not detected yet. So how do you want to go and detect these gravitational waves? Okay. So as I said, there are two mirrors going back and forth in these cavities. And imagine that at a certain point a wave comes and go through the screen. Okay? So space will be distorted, and the distance between the length of one of the arms will be different from the other. Okay? In a oscillatory pattern. Okay? If this happens, you are going to see. So you do you have a big splitter, and you look at the interference of these two lasers. So I mean, the interferences is very sensitive to small differences in the two arms. And when I see a small difference, of course I have to check that it's not an experimental problem, it's not noise, but it's possible to detect the presence of this distortion of space. Now, what is completely amazing, and it's a tribute to our experimental colleagues, is that the experimental precision to observe gravitational waves is amazing. It's about 10⁻21. So what does it mean? It means that to detect these waves, you must be able, experimentally, to measure the difference in the two arms with a precision of 10⁻21. Just to give you an idea, this is the same as measuring the distance between the Earth and the Sun with the precision of one atom. So this, I find it, every time I say it, I find it amazing. Okay. But this is what is required, and this is what is achieved in these experiments. Okay. So what do you see? I mean, just to be... Oh, sorry.
Just I have a curiosity because, I mean, the gravitational waves, which basically it affects, the laser or the mirror?
Well, it's a good question. It's a bit difficult to answer. This statement is mid-gauge dependent. So as in electromagnetism, you know that in electromagnetism you can describe things using different gauges. Here the same for gravity. So there are gauges in which basically the mirrors, maybe it's the easiest, I mean, at least for interpretation, there is a description in which basically this is a force which move the mirror. Okay? But this is not true in any gauge. There are other gauges in which actually is the length, so the mirror stays in place, but actually what is called the metric of space is modified in such a way that the distance is a bit different. So it's a bit, yeah. Of course you get the same result, but the interpretation is slightly different. So what do you observe? Was what people observed almost 3 years ago. So this is a signal in one of the LIGO detector, which is one in Washington State, and this is the other one in Louisiana State. So first of all, so this is 10⁻21. So when I said 10⁻21, this is what they achieved. So this is the precision they have to see. So you see that this is noise. Okay? Because of course you can easily imagine at this level of precision how much noise there is. Everything creates noise. Every seismic activity, thermal activities, the vibration of the mirrors, everything must be under control. So there is some noise, of course. But then you see that there is a clear pattern here. Okay? And what is important for believing in this experiment is that the same pattern is obtained, on the other side of the United States at the same time. So you're quite confident that you're observing something which is not just the movement of something nearby. Okay? So just to be a bit more precise, what are we observing here? So I didn't tell you where these gravitational waves are coming from. Well, they are coming from two astrophysical objects. In this case, most likely two black holes. So there are these two. Okay, first of all, why we look at these objects? Why these are the leading source of gravitational waves? Because I told you that gravity is very weak. So if you want to generate a sizable gravitational wave, you need some big object, but you also need this object to move very fast. Because you may remember that also in electromagnetism, to generate an electromagnetic wave, you need to move electrons or charges, and here you need to move masses. Okay? But of course, the faster they go, the more they generate gravitational waves. Okay? So you want massive objects moving very fast. Okay? So these are two black holes with a mass a bit like 10, 20 solar masses, so somewhat bigger than the sun. And sometimes in the universe there are two black holes which are orbiting each other. Okay, so they are orbiting like the sun and the Earth. So they orbit, but as they orbit, they produce gravitational waves. Of course, also the sun and the Earth produce a bit of gravitational waves, but this is completely negligible. Okay, so in this case, they produce a bit more. And so as they go around, they lose energy very slowly in emitting gravitational waves. Okay. But as they do it, they get closer and closer. Okay. And basically what we observe experimentally is just the very last second before they plunge and form a new, bigger black hole. Okay. So because, of course this goes on for a very long time, but this is much smaller than the signal that we have. Actually, for some other events, some later events that they also observe other events, you can see the ringing going on for a longer time. But in this case, they were able only to observe the last seconds, a fraction of a second before the plunge. Okay, you see that the signal goes up because as they go around, they go faster and faster. Okay, because they conserve angular momentum, so they go faster and faster, and this increases the production of gravitational waves until you form a big blob, a new black hole, and the signal goes down again. Actually, it's very interesting because there is a big community in the field which wants to understand and predict this signal. Okay? It's very important to predict the signal for two reasons. First of all, because you are able to find the signal if you know what you're looking for. Okay? So this is particularly evident, but imagine that I want to discover something which is a bit buried under this noise. Well, if you really know what you're looking for, you can sort of filter out the other things and see the signal, otherwise you don't. Another reason is that, as you can imagine, the correct form that you see here contains information about these dynamics. Okay? So, for example, if you want to know what is the mass of these objects, not only of the single objects, well, you can find that the form of the signal knows about the mass of the objects. It also knows about how they rotate, the spin, and so on and so forth.
So,
yeah.
What does it mean shifted and inverted? So
Yeah,
it's because it happens at the same time, or you have to shift it?
No, okay. So it's there are two effects. First of all, it's slightly shifted, and this is very interesting because it has to do with the fact that, as I'm going to discuss, it takes some time for the wave to go from one side to the other of the United States. And I think it's shifted just because the two experiments that they decide, they calculate the difference between one arm and the other, and so I think the other experiment was, it's just a question of phase, basically. So they superimpose after taking into account these shift.
And they have the same noise level, basically.
Basically, the two, these are really the same. The two LIGOs, I think, they are practically constructed in the same way. There are slight differences due to the surroundings, but they are similar. So you see the importance of having two detectors. Of course, there is not much natural doubt that this is coming from outside the Earth, because it's the same signal in very two different places. Okay, this is very interesting, but this is the beginning. So after that, they observed many more similar events. And of course, this is very interesting because it's the first time that we observe directly not only gravitational waves but also black holes. Now we can start thinking about the physics of black holes. So there is a lot of physics that I'm not going to describe, but you can easily imagine how interesting it is.
Do they also measure a light signal?
I'm going to, yeah, very good, yeah. So this has been a tremendous success because this, in this case, yeah, let me show this. So the question is whether you also see some other signal associated with this event, some light, some electromagnetic signal. Now, back then, without the third detector, which is LIGO, which is a Virgo, so it was not very easy to triangulate in space. Well, the reason it's called triangulate is because you need 3 detectors. So basically, there was not much information of where the signal was coming from. Okay? So you can compare the 2 LIGO detectors, but this leaves these very big bands. So you don't really know where it is in this big globe. Okay? So it was impossible to target to some astrophysical, so to reconstruct where the signal was coming from. But this changed 2 years later, which is like a bit more than a year ago, well, in August. This event, so this is the name that they give to these events. This is the gravitational wave, this is the date. Okay? This was the 17th of August. So at this stage, there were 3 detectors working, and with 3 detectors, you can quite well understand where the signal is coming from. Okay? And now, what you do? You call all the other collaborations with telescopes and various all the detectors which are sensitive to something coming from the sky, and you tell them, look at this particular region of the sky. You should see maybe something associated with this event. Okay? They did. And they found, as I was explaining, some signal. Okay? They see some light. Okay? Light in general, so any frequency of the spectrum from gamma rays to radio. But this means that we're not talking about black holes, because black holes they don't emit light by definition of black. So it's a different kind of event, and it's an event which is called a neutron-star merger. Well, I have to say that I'm not particularly an expert of this, but I mean, a neutron star is a star which is very close, is extremely dense. It's so dense that it's not far from becoming a black hole. Okay? It's basically made of neutrons, and it's kept by the neutron pressure. And this event most likely is the same event, but between 2 neutron stars which collide. In this big splash, you also emit a lot of energy in electromagnetic waves. And so in this picture you see that you emit both gravitational waves, which are here, and also a lot of any form of radiation. And so it was possible to detect gravitational, not only the gravitational wave signal, but also what's called the electromagnetic counterpart. Okay, so again, I'm skipping a lot of super interesting physics. So this is the first time that we see the collision of 2 neutron stars. So we can finally understand a bit better what a neutron star is. This event is what is called a GRB. So it's this flash of light that you see in the sky is also an interesting topic. And so there is a lot of physics here. So I'm going just to choose some particular corner. I just want to stress more than what I did, the fact that there is a lot of physics to explore. So let me focus on on a particular aspect. So the particular aspect is exactly related to what was asked. So now I observe gravitational wave coming from there and electromagnetic signal coming from there. Okay? So the first thing that you can imagine to do is to say, okay, do gravitational wave and photons, light, travel at the same speed or not? Okay? And this is described by this picture. So, so the title of the slide is the name of the gravitational wave event But now the same event observed in light has another name, because it's what is called a GRB, and it has of course the same date. So the fact that these two events observed in two different ways, they come from the same event, tell me something about the speed of gravitational waves compared to the speed of light. Okay, let me explain what this plot is. So on the bottom, okay, it's basically similar to what I was saying before. This is a gravitational wave signal as a function of time. So you remember that the signal becomes larger and larger just before the formation of a single object, and you see that this is happening. Okay, so it goes up. Sorry, this I apologize. This goes up not only in amplitude but also in frequency, because as I approach, I go faster and faster. Okay, so you see it here. So as a function of time, you see that the wave is shorter and shorter. You see it also here. You see it also here that these waves are of longer wavelength until they become very, very fast and disappear. The same happens for this event. Okay. So this is just to say that this moment is the moment of a collision. So you follow the signal until you see that there is no signal anymore, and this, on the other hand, is observed by the Fermi satellite. These are very energetic photons of between 50 and 300 keV. Okay. This was observed in many different experiments. I take this because I think it is the most precise measure, but it's not the only experiment. What you see is a lot of noise, and then a big spike, which tells you that they detected an event. So there is a difference between these two moments, but we think that this is a couple of seconds, and I mean, I'm not an expert of this field, but you may imagine that when there is this big mass, it's reasonable, of course the experts know better, but also to me it looks reasonable that it takes some time for light to go out of this shell of matter, while gravitational waves do not interact with anything, so they go out immediately. Okay? So we believe that this couple of seconds is due to astrophysics. Okay? So the bottom line is that this signal is compatible with the possibility that light and gravitational waves, they travel exactly at the same speed. And notice that this is a remarkable result, because I didn't tell you, but the signal propagates from very far away in the universe, okay, around 40 megaparsec. So this means that it travels a huge amount of years, and the two signals get to us with a difference of a couple of seconds, which most likely is due to the fact that they were not emitted exactly at the same time. So this single event gives a wonderful precision on the measurement of the speed of light compared to the speed of gravitational waves. So it's the precision we get. So this is the difference between the two speeds over the speed of 1 to 2. I mean, the bottom line is that they must be the same with a correction of order 10 to minus 15. Okay, so they are really, really very close to each other. Now, you can say, okay, first of all, do we know this before? Well, experimentally, no. Experimentally, we didn't know much about gravitational waves. Okay? So, I'm trying to explain, in the simplest model of the universe, it makes a lot of sense for the graviton and the photon to travel at the same speed. Okay? So if you studied special relativity, all massless particles, and the photon and the graviton are massless particles, they travel at the same speed. So it's not surprising. But first of all, it's very remarkable that this was unknown before, because we didn't know anything practically. There were some bounds, but not as precise and not as powerful about the speed of gravitational waves. So this was a big jump in our knowledge. So now we know that gravitons move at the speed of light. So let me also mention a couple of things which will become more relevant later. So first of all, well, remind me, so this is the typical wavelength of the signal. So the typical wavelength is about 10,000 kilometers. There is a range, but let's say between 500 and 6,000 kilometers. So it's why I'm saying this, so I anticipate, because in general you may ask, okay, but I know that, for example, if I take light and I look at the speed of light in a material, this depends on the frequency. So better to be sure, so that's why I'm specifying this. So this is a measurement done at this particular wavelength. Of course, if light is in vacuum, the speed is the same at any frequency. But if you are in material, it changes. So let me specify this. Second thing is that, as I told you, this signal comes from 40 megaparsec away. So it's a considerable distance. So just to tell you, the whole universe is like 10 to the 4 megaparsec. So it's it's huge compared to the galactic size. So the galactic size is like 10, 50 kiloparsec. So we're talking about distances which are huge compared to a galaxy. Okay. I'm saying this because I want to stress that the signal travels a considerable fraction of the universe, and it's not something local. It does not come from a nearby star. It comes from far. Okay, any question about this? So this is
this is the only observation, right? So do you have also similar observation for the light and the gravitational wave from other?
No. As you may know, at the moment, soon after these results, the 3 experiments shut off to go through an upgrade. So they will turn off again in a few months. But with so at the moment, it's the only event in which we have 2 things, yes. And it's the only.
So how do they synchronize the 2 signals? Just to kind of out of curiosity.
These I'm not particularly, but I don't think it's, I don't think it's particularly difficult. No. So in a sense, I mean, to the level of a second, I don't think there is not much of a problem. We're talking about 2 experiments on. So actually, this is a satellite, but I think that at this level of precision. So since we don't really know the astrophysics within a couple of seconds. I think if the 2 signals are very close to each other, then we can discuss about it. But at this level, I think it's easy. But of course, we don't know. Okay, so this is one part of the story. Now let me tell you the second part. So I remind you that the topic was observation of gravitational waves and dark energy. Okay, so what is dark energy and why it is connected to this topic? Well, you may know that the universe is expanding, of course, but it turns out that it's accelerating. So what does it mean, accelerating? Well, it means that if I plot as a function of time the size of the universe, so until recently in cosmic time, it was decelerating. So it means that the second derivative of this function is negative. Okay, this particularly is normal, in a sense. Why it's normal? Because if you know that gravity is attractive, so you expect that, okay, if I have an expanding ball, since the various objects want to stay together because they attract each other, so you expect that this is decelerating, okay? So it's like, if you send a stone, it wants to come back, so it decelerates and wants to come back to you. So what, surprisingly, like 20 years ago, people got progressively more and more convinced that the universe nowadays is accelerating. Okay. So the second derivative of the size is called the scale factor. The second derivative of this object is positive. The universe is accelerating. This was quite unexpected. Okay. I remember, I remember being in a similar kind of. I was a student, and I remember I was starting my PhD, and I remember I went to this conference, and of course I learned in my course that the universe was decelerating, and we were trying to measure what is the rate of deceleration, and then I went to this topic, and they were talking about acceleration, so I was a bit confused, but it turns out that I was not the only one confused, because the whole community was shocked by this aspect. Okay, now I'm not going to the evidence, but now the evidence of this is overwhelming. So it's based on many different observations, and each of them is separately very convincing. So we don't doubt about the fact that the universe is a sphere. It's strange. It's strange because, as I said, gravity usually should be attractive. So why the universe is separate? Okay? Now we don't really understand this, and this is our understanding of the universe nowadays. So 4% of the universe is ordinary matter, so which means that the matter we are made of, so matter that we understand. Then there is a lot of matter, which is 20%, which basically is similar to ours, but we don't know what it is, in the sense that does not interact with light, and so it's not the same particles we're made of. It's not part of the standard model, okay? The standard model of particle physics. So this is a particle, most likely is a particle, but it's a particle that we don't know what it is. Okay, so this is one piece of our ignorance. Then there are 76% of additional ignorance, which is dark energy. What does it mean, dark energy? Dark energy means we don't really know why it's accelerating. Okay? Whatever is causing this acceleration, we call it dark energy. Well, so what? Yeah, now I will try to explain a bit better. What is dark energy? Well, dark energy is something. Of course, we have some guess of what it is. It's not but it's something which is approximately homogeneous. So this means that it's not something which falls. For example, it's not that. If I compare with dark matter we don't really know what it is, but it's something which clumps in the galaxy. For example, the galaxy is very dense in dark matter. Okay. Dark energy is something which is smooth. Okay. So it's at least approximately smooth. So it's like some sort of medium which permeates the universe, okay, and is responsible for the acceleration. Okay. So it's just for the students. When they tell you that there is still something to do in physics, this is really true because at the moment we understand 4%. The rest is okay. Well, let me tell you something more about this dark energy. Well, if I ask a random colleague like Jorge, I ask what is the guess, what is dark energy is, most of the people will answer that it is what is called a cosmological constant. Okay? Let me explain what a cosmological constant is. So the simplest explanation is that the cosmological constant is the energy of the vacuum. Okay? So I meant, so when you study any problem in the absence of gravity, you don't really care where you put the zero of your energy. So when you draw a potential in physics, usually where you put the zero is irrelevant because it does not enter into equation of motion. Now, if you put gravity, well, gravity is sensitive to all forms of energy and matter. So in particular, it cares about where you put the zero of the energy. Okay. So you should think about this cosmological constant as the zero of the energy. So in this sense, if I am here and there is nothing, well, there is nothing, but maybe gravity feels there is some energy. Okay? Because it's a little bit. So let me try to be a bit more specific. So it's about vacuum energy. Okay? For people that are a bit more expert, let me explain this. Gravity is described as what is called a stress energy tensor. So this is an object that tells you how a system interacts with gravity. So it describes energy momentum of a system. Okay? It's the same object that you meet in electromagnetism. And in the case of a cosmological constant, well, I mean, since there is nothing here, so the only thing that this should be proportional to is the metric. So like in a Lorentz setting, so basically you want to describe the energy of vacuum. Well, if there is nothing, the only thing that is there is the metric, which is eta mu. Okay. So this tells you that by symmetry, if you have some cosmological constant, the stress energy tensor has this form. So if you remember, this metric is the metric of special relativity, so it's 1, minus 1, minus 1, minus 1, or depending on the notation of minus 1, 1, 1, 1. But what is important is that so what is in the 0, 0 component is the energy. The other components are the pressure. So this argument tells you that, I don't know if it's intuitive or not, but the vacuum energy has negative pressure. So you know, it's a non-dynamical object. So the fact that that negative pressure is, don't think that it's something which, because you know, it's the energy of. Anyway, so this why it's important, because if you write the equation for this object, the object that I was plotting here, A double dot, in general relativity you get something of this form. That is to say something which is rho, the energy density, plus 3 the pressure. And the pressure is negative and it's the same size as rho. So the bottom line is that this is negative for this object. And I mean, apart from the explanation, the bottom line is that a cosmological constant can give an accelerated expansion. So you say, okay, very easy, I mean, we solve the problem. We found immediately the solution. Well, in some sense yes, in some sense not. So let me try, okay, so let me try to estimate what is the size of this cosmological constant. Okay? So because we also measure the size of the cosmological constant, we measure how much it accelerates. Okay? So let me try to estimate. Okay? So you may know that the current description of physics, of fundamental physics, is based on fields. Okay? So each particle is a field, like the electromagnetic field. And each field, each wave is a collection of harmonic oscillators. Okay? So if you want to estimate, so I take each harmonic oscillator, so each wave. So in quantum mechanics, you know that each harmonic oscillator in the vacuum does not have 0 energy, but it has an energy which is h bar omega times 1. Okay? So very naively, okay, I sum over Fourier modes this 0-point energy. Okay, okay, I have to decide where to stop, because if I go to very short distances, this diverges. But okay, let's say, okay, if you do this integral by dimensional analysis, it goes like, sorry, this lambda is not the same as this lambda. This means is the largest wave that you include in your calculation. Okay? So it's quartically divergent. Okay? There is something which goes like the cutoff, the cutoff of your integral to the 4. Now, what is this number? Well, where do we stop this integral? Well, you may say, okay, we know quite well particle physics up to the scales of LHC, of electroweak interactions. So, I don't know what happens maybe at higher energies, because we never explored experimentally, but I don't know, I will put something which of order the electroweak scale, which is 100 GeV, 1 TeV. Okay. Well, if you do this, you get a number of this sort, which has nothing to do with the observed value. Okay? So there is a discrepancy between these two, which is something like 60 order of magnitude. And I was very optimistic because I said that maybe there is something which after a TV this formula does not work, although there is no real reason why this integral should not be pushed to even higher scale and make this discrepancy even more profound. Okay. So the bottom line is the following. This idea works, so it can lead to the acceleration of the universe, but in order to do that, you have to put a number which is completely off to any estimate that you, and not by a factor of, maybe by 10 to the 60. So people say that this is the most wrong estimate in the story of physics. Okay? So it's very difficult to screw up by 60 or something, even if you don't. Okay, so it's the wrongest guess. So, okay, so this is the status, and I have to say that, I mean, I'm trying to be pedagogical, but I have to say that we don't know much more than this, so this is really the status of our understanding. So it works, but you have to put a number which has nothing to do with what you expect. Okay? So for people a bit more expert, there is also the issue that there is no symmetry to keep this number small. So sometimes in physics we are not worried about small numbers, okay? because some small number is what is called stable in the sense that, for example, the mass of the electron is much smaller than the mass of another particle at the top. It's very small. So is the problem? Well, not really, because when you put it small, it stays small. Okay. This maybe does not solve the problem, but at least it's something which is stable under quantum corrections. Okay. So we think that this is much better because okay, maybe this number we don't really understand why it's so small, but once you put there, it stays. This does not work from this. So if you do a theory and you have this number which is that small, anything you change, any loop corrections, anything that happens will pull this number very high. So it's a very unstable, if you want, situation that we completely don't like. Maybe I should mention about this. So, okay, what people think about this cosmological constant? Well, somebody will tell you, I don't know why it's so small. It is true that if it was as big as this, the universe would be completely different. The universe would have accelerated long ago. I remind you that I told you that the universe is accelerating recently. Well, recently means quite recently. No, I mean, the universe started accelerating when the size is a factor of 2 smaller than today. But you know, we know the story of the universe when it is 1,000 millions times smaller. So from this point of view, it's quite recent. If you put a very large number of the cosmological constant, the story is completely different. The universe starts accelerating at the beginning, and there is no galaxy forming, and so people will tell you, okay, we cannot live in a universe like this. I mean, is the good explanation? Well, I don't know, but it's true that we could not live in a universe with a much larger cosmological constant. Okay, so let me. Do I have 5 minutes more?
Yes. Probably 10 because we started very late.
Okay, but I don't want to go. Right, so because then the thing will become a bit more technical, so maybe I will have to quickly go through that. So, but let me tell you the idea that some of us has been investigating. It's very simple, guys. So the idea is the following. So I told you that a gravitational wave travel through the universe, and in particular, whatever it is, through dark energy. We are now studying this propagation. Okay? So there is a clear difference between vacuum energy and anything else. Okay? Anything else, which in the absence of any representation is this pink blob, which is the dark energy. So whatever is there in the universe, which is not just vacuum energy, but it's something, whatever it is, for sure it's gravitationally coupled, right? Because we want dark energy to do something to gravity, so, and moreover, everything is gravitationally coupled. So whatever it is, it should know something, I mean, we should learn something when gravitational waves go through this, whatever it is. So this is the general idea. I mean, let me stress, it's very simple idea. It's very similar to try to study a material using light propagation. So you shoot light and you see what is the speed, if it is absorbed, all this is possible. So it's a typical way in which we study materials, and now we are doing the same for dark energy using gravitational waves. Okay. So, okay, now I will become a bit more technical. I apologize for the non-experts. So I just want to explain, I will be very sketchy, but I just want to convey, so at a certain point you have to describe this blob. And again, we don't really know what, I mean, there are some models, but we want to be as general as possible. Okay? So the idea goes back to works of many years ago, but goes under the name of effective theory of dark energy. And the idea is just the following. Since I don't know what it is, I just decide what are the symmetries of this system. Okay? For example, if I want to describe a solid, I will know that it has a certain symmetry, some structure. and I will impose this symmetry, and then I will write everything possible. Okay? All the possible, in the EFT jargon, all the possible operators which compatible with the symmetry that I have, which are compatible with the symmetry, and I write all of them. Actually, in an effective theory, the operators with the less number of derivatives are the most important ones. And then I will try to see what the experiments tell me. So I will try to measure this object which describe the fluctuations of this system. Okay? So it's very similar, although it's technically more involved, it's very similar to take a fluid and I don't know anything. Okay, I start parameterizing, so I start saying I want to study the physics of the wave, of the excitation of this system, and I start parameterizing things. So in the case of dark energy, so what we think is this is in some sense is an assumption, but you can think about dark energy as some what's called a scalar field, some object which is evolving in time, and evolving in time, it specifies preferred surfaces in our universe. Okay? So this is essentially what I was saying before. So the difference between a cosmological constant and a medium is that the medium is there. So the medium breaks spontaneously Lorentz invariance. So this means that so there is Lorentz invariance, but of course this table chooses a particular frame. Okay? So if I go to another frame in which I move, this is different from. So and this something, this dark energy will choose a frame, okay? Because it's like a fluid, it's at rest in a given frame. Okay? So it will choose some particular slice of space-time. And then, so then what I'm going to do, okay, it's a bit technical, but I'm going to write an action, a Lagrangian, which describes the physics of this what's called a foliation, so a preferred slice of space-time. And these are all, I mean, I don't have time to go through it, but these are all geometrical quantities which are built out of this construction. So you have a metric on this surface. This is the curvature tensor. This is what is called the extrinsic curvature, which tells you how this object bends in the cosmos. These are part of the metric, so I'm really sketchy, I don't want to enter into details. But the idea is that people start writing down these and then check what the universe says. But this is a super complicated formula. This is just, as I said, this is a list of operators. I mean, I don't even have time to explain what the symbols are. But just to give you some idea, these first three operators are the ones that describe the simplest model of dark energy, which is called quintessence. For the experts, it's just a field, a scalar field, which is rolling along a potential. And is described by these three operators. Then imagine that I want to change a bit. So I want to change the speed at which the wave of this dark energy are propagating. This is encoded in this operator. Then there are other operators, and I don't have time to. They have a certain kind of experimental signature, but I don't have time to explain it. And one thing that I want to mention is that at the beginning, I'm going to only consider small fluctuations of this dark energy. So I do a linear approximation. Then, of course, if I'm more precise, and cosmology is becoming precise, I need operators with more perturbations because I want to go beyond linear. Okay? So these are other operators. It doesn't really matter, but what I want to convey is that the measurement of the speed of gravitational waves was able to tell me a lot about these numbers. In particular, this operator, it contains, if you have to expand it a bit, but what is important is that it contains the time kinetic term of the graviton. Okay. So, in short, this object changes the speed of gravitons. It's the same as it happens for light in a material. Okay. So, we measure that this, if it's very, very small, I mean, at a certain point we were interested in dark energy if we were able to distinguish it from a cosmological constant. So if you measure something which is 10 to minus 15, it's very difficult that there will be a way in the future, maybe there is, but at the moment we can treat it to be 0. So this kills completely this operator. Now, for reason that maybe I will skip, but not only you can kill this operator, but also many others, in practice, with the following assumption, that you don't want that the graviton speed is equal to the speed of light only in our particular universe, but that if I change a bit the parameters, for example, the dark matter abundance, you want these properties to remain valid also in that case. So, doing this assumption, you kill a lot of these parameters. Okay, okay, so this just to conclude. So I'm happy to answer a question if somebody is more expert, but of course I don't want to bother with things. Let me, well, another thing that I don't have to time to explain, but it's very important. So I told you that we are obsessed, we don't like the cosmological constant because it's a small number, and I don't know why this number does not become bigger, it should be bigger. So of course, the similar caveat applies to this. So if I say that this is 0, this is 0, this is 0, this is 0, the natural question is, okay, but are you sure that when you put this 0, this choice is stable? Okay, this is something that the community addressed, and it's an important subject because, again, we don't want to create again the problems that we have with the cosmological constant. Okay, this is something that, okay, that I have to skip, but it's an important subject. The last slide is another phenomenon that we studied. In a material, light not only travels at a speed which is different than in vacuum, but also it is absorbed by the material. Okay? Not surprisingly, the same happens for the graviton. So I call this gamma. I realize that many people, when they see gamma, they think about light. Gamma for me means gravitational wave. So I have this blob and the gravitational wave is propagating. So I can imagine, like in a material, that the gravitational wave is absorbed by the material. Actually, I mean, for people in the QFT, so you may remember that a massless particle in quantum theory cannot decay because the only way to decay is to decay to other massless particles in the same direction, but it's not really decay, it's some sort of redefinition. So, what I'm trying to say is that the presence of this material, whatever it is, allows kinematically the possibility for the graviton to decay. Usually, we don't discuss the decay of the photon or light in vacuum. So, the light can decay inside the material, but not in vacuum. The same things happen for gravitational waves. So, in particular, what we studied is the conversion of a gravitational wave into excitation of this material, which I call pi, well, material in important, or a similar effect like this. But these are just situations in which the gravitational wave comes and excite this dark energy, whatever, and it is absorbed. Of course, we see gravitational wave coming, so it cannot be absorbed too much. Okay? So there are limits, and without entering into details, this can be used to put other constraints on this dark energy fluid. This is another operator that I didn't have time, but it's another parameter that can be set to 0, checking that gravitational wave must have a sufficient free path to come to us from the black holes. Okay, so this, I don't want to bother you too much. So in a sense, this I think it's a rich subject. Again, maybe dark energy is just a cosmological constant, so all these parameters are 0 and will be left in the simplest possibility. But I find very exciting the fact that these observations, this recent observation can tell me a lot about the physics of dark energy. On top, of course, of all what we can learn astrophysically from the observations of these black hole events and neutron star events. So let me conclude. What I was saying is that the gravitational wave can probe dark energy like light can probe a material. So this is you can measure the speed of gravitational waves and constrain dark energy models. or look at absorption of gravitational waves in material. So all these and I think there are also possibly other effects that we didn't think about yet. Again, there is this big lambda. So I think this is really a big problem. It's one of the biggest problems in physics. So maybe we didn't understand anything. So maybe this number is completely off the estimate, but it is what it is. And progressively we're going to learn that this is dark energy. But I think anyway it's interesting to use experimental data to approach this circuit. Thank you.
Questions from students?
Which are the application of gravitational wave?
You mean technical? You mean applications for real life or for science? Well, at the moment I cannot think about any. Yeah, these are very, very tiny effects. So I think I think the way you should think about gravitational waves is not too much has to do with everyday life, but so far we observed everything around us using light of different wavelengths. For now, we observe astrophysical phenomena also using another way of another form of transmission of signals. So, I mean, I don't think this kind of transmission of signal would be relevant for everyday life, but I think about it also as a tool to look at the universe. So it's, but I mean, I have to say, for the time being, there is no application. You know, it's always difficult to answer this question because, for example, also general relativity looks completely. The theory of gravity looks quite unimportant for everyday life. Nowadays, for example, it's not very true because, for example, the GPS need gravitational wave general relativity corrections to it. So, I mean, the answer is that at the moment I don't see any. For the future, I don't know, maybe not, but I think they are still scientifically very important.
Questions? Any questions? So I have, go ahead.
I have a very small question about the precision of the LIGO instrument. You said it was 10 to the minus 21. I'm not sure if the wavelength of the laser can be that precise, or what is the wavelength of that laser?
It's a good question, but I'm not sure if I know the answer. Let me answer in this way. So this number is so surprisingly small because I think it's very crucial that you are talking about a large number of photons. In a sense, of course, you may be imagining something at the level of 10 to minus 21, this becomes much smaller than the nuclear size, so it looks completely absurd. So it's much smaller than the wave. On the other hand, I think the reason why you can achieve this is that you're looking at a huge number of photons. Okay? So you're not able, of course, so with a single photon there is no way that you can localize something at this wavelength. But when you're talking about the large gravitational number, I think you can beat these with a large number. I mean, I'm not an expert, but I think this is why you cannot just estimate saying, okay, it's impossible to go below the
So it's an interferometer, basically, right? So what you do is that you measure the difference between the two paths. So then they can be smaller than the wavelength.
Yeah, but not that small because the interferometer goes like 10 to the minus 1.
No, it depends on the. You can go below the wavelength of the light that you're using, way below. But that's actually something that I wanted to kind of build in the lab just to show this kind of experiment because it is kind of an easy experiment.
Not to measure radiation waves.
No, of course not. I will not compete with your guys. One more question?
How do you know that the dark energy is about 74% of the universe?
Good. Okay, so let me try to. Well, in short, so there are various ways, but let me try to explain one. So you see this curve. So this tells you the way the universe expands as time goes on. So now, if I start looking at the very, very far away object in the sky, light come from these objects and it was emitted when the universe was much smaller. So for example, I can look at an object and light was emitted when it was here, or even far away here. So looking at how the luminosity of these objects, I'm able basically to reconstruct this curve. Okay? It's a bit surprising because you know, you can say, okay, nowadays, how can I know what the universe was doing when it was much smaller? But you can use the fact that light comes from these sources when the universe was actually much smaller. Okay? Once you reconstruct this curve, okay, then you know, each one of these components contribute to this curve in a different way. I told you that dark energy or cosmological constant leads to acceleration, while dark energy is another kind. So you reconstructing this curve, you can reconstruct this pie. It's a simplification. Of course, for example, we know a lot about ordinary matter, so we know quite a lot about this 4%. We also know a lot about dark matter, because I told you that dark matter falls inside galaxies. So it's not something which is homogeneous, something which is, so if I look at the various galaxies, I know the gravitational presence of dark energy, of dark matter, I apologize. So all this information together allows me to know this, and we know this quite precisely with an error of a few percent, but we are sort of, yeah, this we know it perfectly.
So, if I understood right, we know that the signal came from the neutron star merger because of the light signal.
Yeah.
And this is the only data that's available. So, what is the possibility that this was a coincidence that there was a light signal exactly at the moment when in Washington and Louisiana there was a gravitational wave kind of signal, let's say, due to something else?
Okay, yeah, good question. I don't really know the answer. So there are also other observations that, well, first of all, okay, I'm completely not an expert, but so first of all, looking at the gravitational wave signal, you know that these are not black holes, because of course there is some sort of difference, because these are objects which are much thicker than they are not inside the Swadeshi radius, so they are objects which are not black holes. So you see these in the gravitational wave signal. So you already know that these signals most likely are not black holes. So you expect some you can estimate the mass of this length, and
But how do you know from how far they came?
oh, this you know. Yeah, we know quite precisely. Even without light, you know the redshift, because yeah, thank you. So I told you that looking at the signal, you can reconstruct. Well, in short, black holes or any binary object is what is called a standard siren. In a sense, if I tell you the mass of this object, you know that at a given frequency how much energy they emit. So if I know the energy that I get, and I know the frequency because I read it, I know how far they are. Okay? So I know how far they are. So I know that now. You look at the signal inside this galaxy, which is at the same redshift. Then, of course, I'm not an expert of neutron stars, but what I'm saying is that both from the gravitational point of view and from the GRD point of view, people were expecting that they are compatible with. Now, it's I mean, yeah, I'm not. I mean, in a sense, there is. Yeah, to which extent we know what kind of precision we know that it's a neutron star, I don't really know. Everything is consistent with that, but this thing will become much more known in the future. There will be hundreds of events of this, and then at a certain point we start. People already think about measuring, for example, the equational state of the neutron star, which enters in the gravitational wave signal. Yeah, but I'm not an astrophysicist, so.
So if there is no further questions, so thanks again. We have some food outside, so please feel free.